Okay, so first we're going to talk about dispersion forces. We're going to start at the bottom, we're going to work our way up, you know, as I call it, the Drake. He stole it from me, obviously. All right, even though he started in Canada, which is literally the top of America, but whatever. What we have in dispersion forces, these are nonpolar molecules, as we talked about earlier, so there's no constant positive and negative area. You know, everything is evenly shared. But even when you have evenly shared electrons, it's like people moving around on a deck of a boat. You know, they might be equally distributed, but every now and again, they might crowd to one side of the boat temporarily. One side, you know, go look at the iceberg that they're about to hit or whatever. And so that is going to cause an area of partial negative charge. And wherever they aren't, it's going to be partially positive. Now, it's going to fix itself as people go running away from the iceberg all over the boat. Electrons are moving around randomly. So sometimes they'll overload a side and make it a little more negative. And then wherever they aren't is a little more positive. So it's a momentary uneven distribution. You know, it's like you're out on the town and you catch someone's eye, you know, across the restaurant for a moment. You have that fleeting moment, whereas the dipole is like, you know, oh, yeah, you're married, like you're locked in. This is a fleeting moment and it passes. But these can happen over and over and over again. And they do. So different parts of the molecule has different fleeting moments of positive and negative induced dipoles. Temporary, they're temporary. They don't last, unlike a polar molecule. Now, what makes dispersion forces stronger? What causes this to happen more? Larger molecules, more electrons, more space for them to roam around in unevenly. That's what does it. So more molecular surface area, which essentially means larger size, larger shape. So for example, if we compare Cl2 and F2, these are both nonpolar molecules. You have chlorine bonded to chlorine, whoops, fluorine bonded to fluorine. I'll even put the dots in because I'm, you know, why not? All right, those are our Lewis dot structures. They're going to share electrons equally. This chlorine isn't going to be any more electronegative than that chlorine, so this is a nonpolar molecule. Same here, this fluorine matches that fluorine, nonpolar. But chlorine is a larger element. It's farther down on the periodic table. It has an extra layer to its electron shell. You know, it's in the third row of the periodic table, not the second. So Cl is larger than fluorine. So Cl2 has more dispersion forces or intermolecular forces. Or I should say it has stronger dispersion forces because it has more area, has more surface area to it. Another example of this would be something like propane versus pentane. That's a longer chain. It has more carbons. It has more surface area. It's a larger molecule. This guy wins again for the same reasons. It's larger. Now the last detail is that shape is also important. You know, that's key. Longer chains. All right. So if we look at something like our pentane from before, same molecule as here, and we pit it against, now we're pitting them against each other. 1, 2, 3, 4, 5. So this has a side chain on it. So it's still 5 carbons. It's the exact same number of atoms, but this one's going to win because it is more flexible. It is a longer chain. So that's why it wins. So branching will lower your dispersion forces. You want one nice long continuous noodle if you can get that. All right, and so that's what's going on with dispersion forces. So we'll just keep working our way up the ladder. So next we will talk about dipole-dipole, if I remember the list right. Oh good, I did, all right.